All right, so the next thing, so now we have this tool. We have this tool in the toolbox about this regression. And we saw that it minimizes, the regression is going to be, if we're looking to minimize the root mean squared error, the regression slope and the regression intercept is the best we can do. That is going to minimize the root mean squared error. But let's actually talk about it. But the thing to remember is that this is the best we can do with a line. And so this all hinges on the fact that the data has a linear relationship, right? And so at the end of the day, we can crank through the numbers. We can kind of, turn the crank, and we're going to get a slope and an intercept. We will always get a slope and an intercept. We will always get some minimum from there. But that doesn't necessarily mean that there is a linear relationship. It's just going to crank through and show. And so it's always good to kind of take a step back and look at the errors. And we're going to introduce this concept of residuals. So we know about the errors because we just talked about that. And we're going to use, like I said, the root mean squared error from that. And so the residuals is just another way of looking at the error. Okay, and it really is that we're going to look at the error in the regression estimate. Okay, and so for every data point that we have, we're going to have one residual, and it is simply going to be the observed y minus the regression estimate of y. Okay, so we're just basically kind of looking. We're looking at we'll take a scatter plot of the error from there. Okay. And so this residual is also going to be the height of the regression line at x, okay, from there. And so we're basically kind of looking at the distance. We're looking at the distance between the best line, right, our predictor, and the actual point itself. And let me show you, and this is a case where a picture really is worth 1,000 words. Okay. Let's see, what did we add to our toolbox? All of those look good, right? So all of those are the same. So we added the fitted values to our toolbox, right? So this is going to return our prediction using the regression slope and the intercept. And then so finally, this is new, right? This helper function is going to compute the residuals for us. And again, it's taking the same generic format of our table X and Y. And all we're doing here is we're getting an array of our predictions using our fitted values function. And we are just looking at the difference between the actual value, the observed value, and our prediction from there. Okay, so that's all that the residual is. And it's just the difference. It is just the difference. So you're going to get positive and you're going to get negative values from there. But okay, let's go back to mid-parent heights. And we're just using the functions that we already have to build up our table. Nothing new here. So these are our fitted values, right? These are our predictions. And then this is just the residual. So this is, you can see, it is simply the child, right, minus the fitted value from there. Okay, and so we can now look at the correlation. And so if we're looking at the correlation, so we're taking our heights table, so we're looking at the correlation between the mid-parent and the child, right? So and we should expect to see some correlation here. So what's the correlation between the mid-parent height and the child? We've looked at that before, and that's like around 0.32. Okay, and then we can, again, this is, and so what I'm doing here, this will be very helpful. This might be very helpful for you working on your projects and looking on visualization. So what did I do here? So here's the table that I have, right? It has our 4 columns in here. And so I've done the scatter plot, but I've passed in the mid-parent column, okay? So when I pass in a column to scatter, it's going to take that as our X value, and it's going to plot all of the other columns. This is kind of the default. If you just pass in the one here, it is going to compare all of these columns. It's going to do basically the scatter plot with X being our mid-parent height, right? It's going to compare all of the other columns. In this case, it's going to be our child, our fitted value, and our residual. And you can see, right, this plot looks a little different than our normal one because of scaling, right? The default will try to kind of scale your plot accordingly. And so, you know, the top part looked a lot fuller usually, but now our residuals, right? Our residuals are just the difference. And so they're going to be clustered around 0, and they're not going to be that far from 0. But the scatter plot, if you give it one axis, it will plot all of the other ones, right? And so you can see here's child, and then fitted value, and then residual. So it's going to plot all of them from there. And you can see, right, the residuals are all around 0. And looking at the residuals can give you a good indication of how well this line is actually fitted. And so in some sense, I wanted to show you this plot like this because so here's our fitted value in gold, right? And really kind of what really is the residual, it's basically if you're taking your fitted value and you're kind of rotating, if you're rotating that fitted value so it lies and scaling it appropriately so that it basically lies perfectly flat. So you're rotating the whole thing so the fitted value has a slope of 0. And you can almost kind of see that, right? If you kind of look at the gold line and you just kind of tilt it down a few degrees, you get the residual line down there from there. And you can see it basically has the same shape. And so when you kind of look at the plots, and so I'm just going to show you the plot individually here, right? So here it is, you know, in its not squished scaled glory, and then here's the residual, okay? And so what do you want to see? You want to see if if the linear regression is you know, if the relationship really is linear, your residuals will look something just like this. And so what do you want to see? You want to see basically a unassociated blob. All right, that is a technical term, but it's going to be, you know, centered around, it's going to be around 0, and you're not going to see a discernible shape to it from there. And this is you know, a good blob from there, right? This is a good indication that this relationship really is linear from there. Okay. Any questions? Okay, so the residual plot is another tool that we have in our toolbox for seeing if this relationship really is linear. And as we say, right, it's, you know, by looking at the scatter plot, the scatter diagram, the residuals, for linear relations, the residuals should look like an unassociated blob. You shouldn't see a discernible shape to it. It will, however, if you do have nonlinear relationships, it will show patterns. It will show some type of patterns, and that will be a very, so the residuals isn't showing you kind of any information that isn't there, but it's showing you in a format that makes it much easier to visually discern any patterns from that. And we'll look at some examples that aren't necessarily perfectly linear to show you kind of what those are. But this is a good sanity check to see whether the regression is appropriate or not. And so what do you want to look for? You want to look for anything that has any curves associated to it, any changes, any trends, right? If you see the kind of moving up, moving down, and then changes in spread, right? And so for some part of the data, is the errors more tightly clustered around 0? For other parts of the data, is it more spread out? Any outliers, and basically any other patterns that you see. And so let's actually take a look at an example where you might see some of that. Okay. All right. So we've added now, we've added our residuals helper function to our toolbox. And that's just the code that we looked at in the last demo. And so now we added a plot residuals as well from there. Okay, let's pull back and look at the demographics. We saw that it was very highly correlated. And if we now look at the residuals, if we look at the residuals, now you can see, right? And so let me pop back, right? Let me pop back because here was our Galton data, our mid-parent height, right? You can see that there's not really a discernible shape. It's just kind of unassociated. Here, you can see, right? You know, there definitely seems to be a little more association from here, right? And so in particular, as we move to the right, the cluster looks like a little bit more spread out, right? You almost kind of, if you look at the data, it almost kind of looks like a funnel. It's like a kind of an alligator's mouth, you know, an alligator's mouth pointing to the right from there, as opposed to looking at this, right, where it seemed the error seems pretty uniform across all the different heights. Here, it definitely seems like it's going out a little more from there. Okay, and so that's kind of that's something to kind of you know, keep in the back of your mind when you look at these things from there, right? It's still highly correlated. It's still highly correlated, right? Remember the correlation was like 0.81. But looking at the residuals, it seems to be a better predictor, you know, in the lower college percentage than the higher college percentage. And I guess, you know, kind of intuitively, that kind of makes sense, you know. I don't know, intuitively, I don't have any solid proof or theories why that is, but it kind of makes sense to me. Okay, and so, all right, so before we go, there's one last thing that I want to talk about. So you kind of look at it visually, but we can actually we can look at some numerical properties of that, right? And so we can kind of leave off with this kind of discussion question. And so looking at the residuals, what should the average of the residuals be? What should the average of the residuals be? And does that depend on whether the scatter diagram is linear or shows a nonlinear pattern? So you can kind of think about the two that we looked at, the demographics one and the Galton data. So what should the average of the residuals be? And does that matter if the relationship is actually linear or not? So to take a moment to think about that. I won't send you, just because we have a few minutes left, I won't send you into the discussion groups, but I'll pause the recording at least. All right, while you're thinking about that, let me set up the last part of the demo that I want to show you, and that's where we'll end today. And so here's our demographics, right? And we saw that there's a high correlation, but you can see that the error definitely kind of gets a little more spread out from as we go on. So let's take the average. So we're going to take our residuals and we're going to take the average. All right, so lock in your prediction. And if we actually run this, we see that the average is 0, okay? And if we look at the correlation, right, even though the data is correlated, right, we're looking at the correlation between college and media income. We saw the data is correlation, but the correlation between the fitted value, like our prediction, and the residual is going to be 0. Okay, and this kind of makes sense, right? Again, from the idea with this error, where we're picking this root mean square error. So some of the residuals are going to be above, and some of them are going to be below. But when we take the average, that's going to be 0, and that turns out that this holds through. That the average of the residuals will always be 0. And that actually holds regardless of what the scatter what the scatter plot of the residual looks like. And it's just, and the kind of rationale behind it is just the same, that because of the, for the same reason that the average of the deviations from the mean is always 0, right? Because we're taking the average. Since we're taking the average, the things that are above are going to be canceled out by the things that are below. Otherwise, we wouldn't have the average, right? So it is not any deeper than that, from that. And that is, we are out of time, and that is a perfect stopping point. I love it. All right, so we'll pick up where we left off.
All right, so we talked about regression for a while by now, okay? And I would say that we started off talking about how, okay, let me get to that English, okay. Yeah, we started off talking about how to think about regression in the first place, right? Like talking about correlation, coefficient in the first place, and then think about what regression is really doing, the linear regression measure. And so that's how we started with topic 25, okay? And then we move on to talk about least squares, okay? So that's the theoretical foundation of why linear regression works, okay? So make sure that you make that connection in your head. And then I guess Thursday, Jason started on talking about regression diagnostics, okay? So this is after you have done your regression, okay? So remember, whenever we're doing regression, there are a bunch of assumptions that we're making. So we better check what we usually call diagnostics, not only for regression, in many other statistical data science models, you will have diagnostics, okay? So the diagnostics are all centered around what kind of assumptions you have made, okay? So for example, for linear regression, okay, let me actually just open the slide so we can do a little review of what we covered last week as well, okay? I guess the first thing is about the residuals, right? We define residual, okay? And then we have certain ways to check residuals, right? Like doing a residual plot. That would tell us how roughly, right, the residual looks like, okay? And then for that, the residual plot, okay, so just to recap here, based on the assumption that we have for the regression model in the first place, those residuals, they should look like an associated blob for linear relation. Okay, so you remember the ones that we have seen in the demo, they're just like randomly scattered around, okay, around 0. Okay, so 0 is another key value in this case, right? The average value of the residual should be 0. Okay, that's also how it's built into the assumption of the model, okay? But then of course the residual plot can tell us certain things, like if you start to see, especially we highlight here, if you are able to find like curves, trends, changes in the spread, outliers, or any other patterns, that might be telling you that the diagnostics of the residual plot might not be passed, okay? Meaning that yes, you can always fit your linear regression if you want, but might not be a good one to be fitted, okay? So that's always important. So I would say that related to what you're doing for your project, make sure that you check that if you're doing a regression analysis, okay? And then whatever the diagnostics shows could be a limitation of your work, okay? But of course, if you want to check in with us to see how you can prove it, great. I'm just saying that right now, I guess, given the interest of time, we wanted to make sure that you do need to check those diagnostics, okay? And then, but all of our projects, I think, are working with a few variables, so maybe there's not much we can improve in terms of modeling, but at the very least, you should address those limitations. Yeah, there's residual, or like I would say, diagnostics that might not look satisfactory. You will term them as limitations of your study. Okay. So then we went on talking about properties of residuals. Okay, so this discussion question, remember, is, well, the average of the residual should be 0, because that's how we really define how the linear regression is going, right? You get a cloud of data, right? You're trying to fit a best fitted line going across it, okay? And then in theory, if the line is working on really well, then you probably will have, like, I don't know, half of the points are above the line, right? Half the points below the line, and the distance, right? The distance of what we're doing is what we call residual, if you remember, okay? And then that's how we're able to figure out whether the residual plot looks good, and then that's also because the average of the residual should be 0, okay? And of course, the residual plot tells you more than that, okay, about like any kind of nonlinear pattern. So that will be other important things to look for, okay? So I think we ended here last Thursday, like doing a demo of figuring out the residuals in practice, okay? And then like we're saying, the average of the residual is always 0, no matter how the scatter plot looks like, okay? And so that's a very important property of residual, and then it will be part of the diagnostics, as we're saying. Okay, so now we're ready to talk about something even more interesting than just looking at the residual, okay? So remember, when we first introduced linear regression, we're having this predictor variable y, right? And then the outcome variable, predictor variable x, and then the outcome variable y, okay? So what we're saying back then, if you remember, is trying to say that, well, if my x can be a really good predictor, I should be able to explain a lot of the variation of my outcome, which is y, by my x predictor. Okay, so back then we talked about, okay, that will be something good to be captured. And then now we're ready to, since we have talked about how to do linear regression and various diagnostics about it, now we're able to actually quantify, okay, what we really mean by that. Okay, so again, the goal, as you can see, is that if I want to have a really good prediction, I want to use a predictor that can explain a lot of the variability or variation in the outcome variable. Okay, so right now, like I said, we're ready to define it more formally as well as quantify it. And you will see that it again goes back to our old friend of correlation coefficient. And that thing is really helpful, as you can see. Okay, so to get us started, we're just going to do a really quick review of correlation. Hopefully everybody is on top of the material. Okay. So the correlation coefficient measures how clustered the points are about a straight line. Okay, so remember, there are certain ways that we actually, like expression that we use to calculate the correlation, but don't forget that the correlation is trying to, well, not only, I guess here, measures how clustered the points are, but also just like the linear relationship between the two, okay? And we have seen examples, if you remember, that if like you can see a general like a positive trend of going on, right? Like say for example in the data cloud, so you know that, well, the correlation is probably positive because of the positive trend, okay? But then the correlation, the magnitude of the value of the correlation, remember, is trying to measure how close those data points are to the line that you're thinking about, okay? So you could have positive straight line going on imaginary through the data cloud, but then if the data points are like kind of scattered away, okay, from that straight line, then that tells us that the correlation is weak, okay? But if they are very close to that straight line that you're thinking about, then that shows that the correlation will be high, okay? So again, correlation is talking about linear relationship. It's the value of it, the absolute value of it tells you the strength of that linear relationship. So that's what correlation is trying to capture. And we know that we actually need to use the correlation, which is the little r, right, to figure out the slope of the regression coefficient, okay? So don't forget that the correlation, we first of all define it, but then we use it more often than not, I guess, in the regression setting of how to figure out the slope value, okay? And then of course, once you get the slope, you can get the intercept, okay? So, so now, like, let's see. So like this statement is kind of vague, like I said, it just how clustered the points are. We know that if they're like pretty much all on the straight line, then the correlation is 1 or -1, right? Depending on the direction of the line. Yeah. But now we're ready to quantify this statement, okay? And once more, I just want to bring your attention that when we try to quantify this statement, we're really trying to evaluate the linear regression model that we're doing, okay? So you can imagine that if I have like a straight line going through the data cloud, and then if the data cloud is, like the data points are close to that line, that probably gives you more confidence of the regression line, right? Like you see that the residuals are not too far away from what you have predicted, right? What you have estimated on the real line, on the straight line. Whereas if the data points are far away, you might be, a little bit worried about whether they're like, it is a really good thing that you're using this line. So we're trying to use this as a motivation, okay? And then we're trying to link this to the correlation concept that we have learned before. All right, so let's look at a demo, and let me show you what we mean by that, and then we can continue with the next topic. Okay. Oops. Okay. Let's hope this works. Let's see. Okay, it does. Okay. All right. Okay. So remember, what we're trying to say is that we're trying to quantify how clustered the points are about a straight line, okay? And that straight line invariably is the linear regression line that we have in mind. Okay, so put that into the background and see what we're gonna get. Okay, so now as you can see, we've been doing a lot of different functions. Okay, so some of this you have seen it before. Like remember, we use standard units, and then from there we can compute the correlation, right? And then don't forget with that we're able to get the slope and the intercept. Okay, so those are from I guess 2 weeks or 2 lectures ago. And then most recently, right, in order to figure out the residuals, we also have a function called fitted values. Okay, so that's predicted values pretty much, okay, of what you have given your slope and the intercept. And lastly, residual is defined to be, the predictive, I think the observed value minus the predicted value. So you wanted to make sure that we also have a function of returning the residuals. Okay, so all of those, you would just load it. And I would just say that also, if you're doing this for a project, you can pretty much copy and paste all of this, okay? But make sure that you know which function is for what, and then use it correctly, okay? And the last thing we add over here is that we remember last lecture, we also talked about the residual plots, okay? So we can also write a function of doing that. It is pretty standard in the sense that we are trying to create a table, as you can see, right? And then use the scatter plot method in order to plot the residual. Okay, alrighty, okay. So for us to get a sense of what we really mean by the cluster, okay, so here how clustered the data points are, we're gonna also define a new function called plot the fitted value. Okay, so the fitted value is the predicted value that you're gonna see. So we're gonna create a function like this. It's also, again, you create a table and then you try to use the scatter method to do the plotting. Okay, so those are the basics. Again, many of this have been introduced before. Okay, we're adding more of our toolbox, right? Like all of the different functions that we're able to do. And a lot of times one is built on based on the previous ones, right? Like we need the standard units first to get the correlation, right? And then we need the correlation to get the slope. We need the slope to get the intercept. So you can see that all of the functions within them, we're actually calling the previous functions. Okay, so make sure that all of these concepts are connected, your own knowledge structure, as well as how things are being performed using this techniques. Okay, all right, so let's come back, okay, finally to the Dalton height example, so we can talk about what we mean by the measure of clustering. Okay, so the heights, okay, so here don't forget we have the predictor, right, the mid-parent height, okay, the observed data, okay, the child's height, okay. The fitted value is after we have fit, the regression line, right? And then we have the predicted or fitted value based on the regression line. That's pretty much for any X you have, you just find the value on the straight line that you're fitting, okay? Meaning that for a particular X value, we do X times the slope, right? And then plus the intercept, then that will give us the fitted value, okay? And then lastly, from there, we define residual, okay? Meaning it's the observed data, observed value here minus the fitted value for each record. Okay. All right. So now we have a table, okay, of 4 different columns: the predictor, the observed data Y, okay, the fitted value Y, and then the residual for each record. Right. And like I said here, for this demo, we're trying to quantify the statement, right, of how clustered the points are about a straight line. Okay. So how are we going to go about it? We're first of all gonna plot the fitted value. So this is the new function that I mentioned, okay? And it's nothing really fancy, as you can see here, right? Like pretty much you have the mid-parent on the x-axis, okay? Y-axis is the child's height. Either the the blue color for the observed data, right? Or the yellow one for the fitted value, okay? On the y-axis, okay? So what we're doing, so this is the straight line that we have fitted, okay? So not surprisingly, the fitted value is lying on the straight line. There's some, like it's not a continuous because we're actually fitted for each record, right? So like say here, between this record and this record, between this fitted value and this fitted value, there are no, no mid-parent height in between, right? That's why we don't have that line. But a lot of times, if you remember for the linear regression, we're just going through a straight line just to demonstrate what it means, okay? But when you're trying to do the fitted value, because the fitted value is based on the actual records, right? So if you don't have any records in this particular range, then you will never get any points over there, okay? But regardless, this dotted line, okay, should overlap with our regression line, okay? And then here, we're just trying to show you that this is another way to show this. And remember, we can always get this once we subtract it, right? To get the residual, we get the residual plot like what we did before. Okay, so this is, we're plotting the fitted value because as you can see here, we're trying to quantify how clustered the points are about the straight line. Okay, and this straight line is being, as you can see, expressed by this dotted line of the fitted value. Okay, so we're trying to put these two together. So pretty much what we're trying to do is that if you look at this plot, we know that this dotted yellow line is the linear regression line that we're fitting, right? And then we're trying to quantify how clustered those actual data points are around this line. Okay, so we're putting everything into this visual and then trying to figure out what we do. Okay, so let me show you something maybe a little bit surprising, and then once we get through it, we might be able to maybe go back to the math to see if it does make sense in theory as well. Okay, so what I'm proposing, okay, is creating or calculating the predicted values, which is, you know, the fitted values. I'm trying to compute the standard deviation of it. Okay, I'm also trying to compute the standard deviation of the observed value. Okay, without doing any calculation first, I guess if you look at it, which one do you think is going to be larger? The standard deviation. Okay, so the first one is the standard deviation of all of the blue dots. Okay, and that's the predicted standard deviation. Okay, and then the observed the blue dots are the observed standard deviation, right? Because that's the observed data. We're trying to get the observed standard deviation. The prediction standard deviation is the standard deviation of the fitted value. Okay, many of them are overlapping. Okay, as you can see. Okay. So my question for you is that before we're doing any calculation, as you can see, we're using the np.std function, okay? And so it's not surprising, like it's not something really fancy, but I do want you to think through which one do you think is going to be larger? The standard deviation of the predictions, which is on the fitted value, or the standard deviation of the observed data, which is the blue dots. Standard deviation, don't forget, is measuring the variability. Okay, so between those two, what are your thoughts? Either you can speak up or type in the chat. Maybe you can just say, okay, I'm just going to ask, which one is higher, the predicted standard deviation or the observed standard deviation? Anyone? In the chat, maybe. Standard deviation is the variability, okay? And which one is more variable?
The observed.
Yeah, the observed, right? Yeah, thanks. Yeah, so the observed, as we can see clearly from the plot, okay? But also just like conceptually imagine the observed data is whatever it is, okay? The fitted value that we're doing, again, is the best fitted line that is going through the data cloud, okay? So the fitted value is, as you can see, like I said, all of these are like duplicates, right? For all of those records, they're all at this mean. Okay, so that's why you're going to have many duplicated values on the straight line, because in fact, when we're trying to compute the standard deviation of the two sets of data, they should have the same number of observations, right? It's just whatever the number of observations are. So as just discussed, okay, so the observed standard deviation is going to be larger, so not surprisingly, so let's just compute them both, okay? So the predicted one is 1.145, 1.148, okay? And the observed is almost, I don't know, 3 times more, okay? 3 times as large as the, of the predicted, okay? So maybe you'll be wondering, why do I care about that? Again, we're trying to quantify how clustered the data points are, okay? So standard deviation is one way to measure the variability, as we know, okay? So now I'm gonna show you a seemingly surprising result, okay? So if I do take the ratio of the standard deviation of the predicted values, okay, with respect to the standard deviation of the observed data value, which remember we're saying that one is 3 times more than the other. So like when we take that ratio, it's about 0.3-ish, okay, 0.32, okay? And the surprising result I'm showing you here is that it is very, very close to the correlation. Okay, to the correlation of, oh, we're not even fitting the line in the first place, right? Remember the correlation, we only need to know the standard units of the two variables, the predictor and the outcome, right? and then we're able to get the correlation. Okay, so I'm showing you this for now. Okay, if you're not convinced, let me show you another example. This is just a hybrid car data set. Okay, we have a vehicle type, the make here, MSRP, acceleration, measure, MPG, and class. Okay, and what we're doing here, okay, is, well, I'm fitting the acceleration. Okay, let me see. I'm using the acceleration as a predictor for the miles per gallon. Okay, and here, as you can see, that is a downward trend, right? The data points, as you can see, well, we don't have that many compared to before, okay? But also maybe there are some deviations going on, like if you were to do a residual plot, let's see over here, okay? So again, well, the expectation is on 0, so that's all good, okay? And it seems that if I look at it, okay, this might be suggesting that the regression line might not be a really good one to be fitted. Okay, so this is one type of like what we're saying that you should be looking for, like curves or any kind of like fanning effects. Okay, so here it looks like, okay, if the acceleration is low, there are more variability. Okay, if the acceleration value is high, there are less variability of the residual. But we know that for the residual, or like for a residual plot as a part of diagnostics, we know that we want to see a residual plot that we do not see any kind of trend. Okay, so this one might be suggesting a little bit. Okay, but let's don't worry about that now, because for the goal, if you remember, I'm trying to show you that the correlation of the correlation value will be actually the ratio of the two standard deviations that we talked about. Okay, so here I'm doing the standard deviation of the fitted value, remember, over the standard deviation of the observed data. Okay. And when I do that ratio, again, it's very close, but of course, in this case, the correlation is negative, okay? But the absolute value of it is, well, in this case, actually exactly the same. Earlier, it's a little bit discrepancy, I think in the, I don't know, the 20th decimal point, but this one, they're exactly the same, okay? So the conclusion we're trying to show you here, okay, maybe you can like buy this idea first and then maybe ask me questions of why later. No matter what the shape of the scatter plot, okay, the standard deviation of the fitted values is a fraction of the standard deviation of the observed value, okay? And the way that we have done it, as you know, in Python is that we're able to compute the standard deviation of the fitted value, right? Put it aside, okay? We're able to compute the standard deviation of the observed data, the outcome variable y, and then we take the ratio, and then regardless whether you have a positive correlation or a negative correlation, you will get the ratio of these two as the absolute value of the correlation. Okay, and that is, so one other way to put it, this is the SD of the fitted values is the absolute value of R times the SD of the outcome variable. Okay. This, I would say, maybe comes as a surprise, like, well, why we would have, like, say, the fitted values, we compute the standard deviation, and then for the observed, we compute the standard deviation. How come the ratio exactly or very close to the correlation in practice? Okay, the absolute value of the correlation. Okay, so that actually will be a question that I really want you to think through. Even if you don't ask me, I'm going to ask you, I guess, in this case. And I do want you to take a moment, and again, I would do a breakout room for that. And my suggestion will be, if you go back to maybe the last 2 lecture slides, okay, to see how related the slope, as well as, I guess, let me put it this way, how are the correlation is related to the standard deviation and, I mean, the standard deviation of the 2 different values, okay? So I guess in particular, 25 will be more relevant. So I would just say that feel free to check that out. And I will do a breakout room just to get everybody start thinking about all of this. So, okay, so I'm showing you the next slide, which is just repeating the result on the slide instead of on the demo, okay? So what we have observed, like I said, is that this SD, the standard deviation of the fitted values, is a fraction of the standard deviation of the observed, okay? And in particular, that fraction is the absolute value of the coefficient, correlation coefficient, okay? So any thoughts? Like, where do we see this before? Like, say, you know, the ratio of the standard deviation seems to be like working together with the correlation coefficient. Where do we see that, anyone? Or like based on your discussion in the breakout room, did you have any aha moment of why this is true when we demonstrated on the demo. Anyone? Okay, so the ratio, okay, we're talking about the ratio of the fitted values over the ratio of the standard deviation, okay? So if we come back to this one, so this is topic 25. I don't know if everybody got the chance to get, or maybe you remember the expression deep in your heart. So this is where we have seen at least some kind of R and standard deviations working together, okay? And that's how we actually come up with the slope, okay, of the regression line. So remember, correlation coefficient is still relevant, okay? And then when we're trying to get the slope, okay, and in particular, we're using R times SD of Y over SD of X, okay? Whereas right now, what we're talking about is the SD of the fitted value over the SD of Y, okay? So it's not exactly the same, okay? It's not exactly the same as what we have seen before, okay? But I want to bring your attention that the SD of Y here in the numerator is what we have here in the denominator, okay? But what's different, like not only like the order is flipped, but also here we're talking about the SD of the fitted values, okay? Whereas here we're talking about the SD of the X, which is the predictor, okay? They seem to be irrelevant, but I would just want to draw your attention to how we can relate the SD of X with SD of fitted value, okay? So remember, the fitted value or like the predicted value that we have done. So maybe is there be another, maybe, yeah, maybe we don't have like expression over there. But remember, oh, okay, we have here, sorry, just up here. The estimate of Y, which is the fitted value, okay, we're using them interchangeably, okay? It is the slope times the X, okay, and then plus the intercept, okay? So if you think about it, slope is going to be whatever a constant that you compute, okay? Intercept is another constant that you will be able to compute from your regression line, okay? What this is saying, and we're trying to emphasize when we first introduced linear regression, is that the regression is only talking about on the mean, okay? And then moreover, if this is a constant, okay, this is a constant, the variability of X is kind of translated into the variability of the estimated Y, okay, through the slope constant. Okay, so that will be the main math behind, okay? Like I said, it's not required for you to really derive all of the steps, and that's not our goal, and we're not showing the steps either. But I just want to show you that we did in the past talk about the ratio of the observed Y over the fitted Y, but not exactly in that format, okay? We're talking about the SD, the ratio of the SD of the observed over the SD of the predictor, okay? What I was trying to say is that here, okay, it is telling us something related, like how X is related to the fitted Y or the estimate of Y, okay? And then it's not a surprise, I guess the bottom line I'm trying to go across here is that it's not surprised that this ratio is R squared, the absolute value of R, okay? And this is one feature of how linear regression comes up, okay? And for us, more importantly, I guess, than this method or than this particular ratio result that we're showing is that we wanted to make sure, okay, so the bottom line, which we're going to lead to the next topic here, is that we want to make sure that this ratio is high, okay? In a sense that, well, we know that if the correlation is high, then the fitted value probably, the linear regression probably will work well, okay? We know that, well, they're closer to the straight line that you think you would go through it, and that is manifested by the absolute value of R, okay? If it's larger and closer to 1, then we know that, well, the fitted value will be not very far away from the observed value, okay? And that brings down the residual, right? And then that gives us more confidence in terms of how the linear regression is doing, okay? So here we have talked about this ratio as R, absolute value of R, okay? And next we're gonna talk a little bit more about, well, instead of working with standard deviation, we can also work with variance. Okay, so again, variance is the square root of the standard deviation, or like standard deviation is the square root of the variance. And we're introducing here mostly because, like I said at the beginning of today, is that for us, we want to use a predictor that can explain a lot of variability of the outcome. Okay, so while SD is standard deviation is one measure of variability, but the math doesn't work as well if we work on the variance. So I'm going to introduce the variance aspect of this, and then they're related, of course, because variance is just the the square of the standard deviation. Okay, so let me new one. Okay, all right. So this part of the lecture is very related to what we just talked about. Okay, but right now we're trying to put it into a variance decomposition concept. So the variance of the fitted value. Okay, this is what we know already. SD of the fitted value over the SD of y is the absolute value of r, right? And then if we take the square on both, on the numerator and the denominator, and also on the right hand side, we get the variance of the fitted value over the variance of y, which is r squared. Okay, so this is algebra. Okay, and like I said, we focus on variance because later on you can see that the math works out even better than the standard deviation, but they're highly related, right? They're just like a square root and squared relationship between those two. And what we're saying here is that, well, we're just taking the squared on everywhere. So we're able to get the variance of the fitted value over the variance of y is r squared. Okay, so imagine earlier I was saying that, well, the higher the value of the absolute value of r, the better our fitting is being done, right? Because you can see that, well, the fitted values will be pretty close to the observed value. Okay, so in other words, we're now trying to explain all of this concept in terms of variance. Okay, but then we have the square term over here. Okay, and again, the higher the value of r square, the higher the value of the absolute value of r, the higher of the value of r squared as well. Okay, so at the end of the day, we want to have a high value of r squared. Okay, and what we mean by that, putting into plain English, is that the variance of the fitted value can explain a lot of the variance of the y. Okay, so this r squared inevitably going to be between 0 and 1. Okay, if r squared is very close to 1, then what we're saying is that the variance of fitted value is very close to the variance of y, right? So whatever is not being explained of the variance of y is very little. Okay, when that is very little, what that tells us is that the linear regression is able to explain a lot of the variability of the y already. Okay, so that's what we mean by, well, that's probably a good model to be fitted. Okay, on the contrary, if you have r squared to be very close to 0, okay, that is to say that the variance of the fitted value, okay, can only explain very little of the variance of y. Okay, in other words, much of the variance of y cannot be explained by the variance of fitted value if r squared is small, close to 0. Okay, when that happens, well, you probably want to find another better predictor, because you do want to use your predictor that can be explained, that can explain a lot of the variance of y. Okay, so that's the concept and then the reasoning behind. Okay, so if I do one more step of math over here, okay, so the top is what we know, variance of fitted values over variance of y is r squared. Okay, it's actually equivalent to say that the variance of the residuals over the variance of y is 1 minus r squared. Okay, so this statement, as you can see, is that we're saying the variance of y has two parts. Okay, it's one part of it is the variance of fitted values. Okay, the other part is the variance of the residuals. Okay, they add up to the total. That's why they have this math relationship. Okay, so right now I'm telling you this is a fact. Okay, but as you could imagine, soon we go to the demo, and then I will just demo to you again, because again, once we fit the regression line, right, I can compute the variance of y, no problem. I can compute the variance of fitted value, no problem. I can also compute the variance of the residuals, right, once I get the residuals. So I can show you that they do add up to, like, say, the variance of fitted values and the variance of the residual, they add up to the variance of y. And once we get that, like I said, hopefully, it starts to make sense to you of why we really want to have a high value of r squared. Okay, like I said, the variance of the fitted values is what's being captured by the model. Okay, if that is a big chunk of the variance of the outcome, then that tells us that our linear regression model is able to explain most of the variance of the outcome. Okay, And we do want a model like that, right? Like you do want to figure out like a predictor that can work really well. So whenever I'm doing prediction, I will have high confidence of how good the prediction is going to be, right? As well as how much the regression line can explain the how the outcome is behaving, okay? So with that in mind, let me just double check that we get to the part of the demo, okay? Yeah, it was not showing up. Let me see, is it? Ah, okay. Maybe I just need to show everything here because there's a, yeah, anyway, it's not the best practice of doing math using slides. But anyway, so here, just to bring us back to what we know already, the average of the residuals is 0, okay? And now we know the relationship, right? Between the variance of residuals and variance of y, that ratio is 1 over r squared. So what this is also telling us is that if I'm able to get the standard deviation of the residuals, it's going to be square root of 1 minus r squared times the standard deviation of y. Okay, so all of them are just like right now, I think, maybe lumped together in your head. But like I said, all of those can be computed. Okay, once we are able to fit the regression line, we can compute the variance of residuals, we compute the variance of y, we can compute the variance of the fitted values, right? So we're able to justify, and I'm going to just show you in a second why that is true. And hopefully that can make you feel comfortable that whatever we're doing right now does make sense, that you're able to use this kind of method in your project or future work. Okay, so as usual, we load all of the necessary functions. It's a lot, but like I said, we're recycling them, okay? It just like the list just grows longer and longer because we're using so many different, we're learning so many different new concepts and how to compute them. And it's always a good practice to write them into functions so we can always use them more easily, okay? Alrighty, so the variance decomposition, we come back to the Galton data set. Okay, so this is already just like what we did before, right? We have the mid-parent, that's the predictor. Okay, that's the X. Okay, the child column, that's the Y. Okay, the observed Y. The fitted value is the estimated Y. Okay, the fitted predicted Y. And then the residual, right, is whatever the difference between the observed and the fitted. Okay, all right, so let's do some plotting. Okay, so this is what we did before. Okay, we have the channels, and that's how we were talking about the relationship between the standard deviation, right? Like we first of all noticed that the standard deviation would definitely be larger for the observed compared to the predicted, and then we realized that that ratio becomes the absolute value, right, of the correlation coefficient. Okay, so right now we're trying to, okay, like I said, we already talked about some of the results like mathematically in the slides, and now I'm trying to demonstrate it using Python to justify it. Okay, so what I'm doing here is nothing fancy, just add a vertical line of showing where the mean, the average of the observed data is. Okay, so half of them, like not half, like about half, around half of them above, around half of them below. Okay, so the variability, okay, I plot the mean because if you remember how we actually compute the variance in the first place, we're looking at how each observation is from its mean. Okay, we take the squared of that and then take the average of all of the square values. So that's why it's important to think about the average. Okay, even though, well, we're going to use Python to do the calculation for us, but variance is trying to capture. So variance for the child, the observed child data points, there will just be the average square distance of each record to this mean. Okay, all right, so with that in mind, well, we don't need to do too much complicated stuff because remember, the standard deviation is the square root of variance, right? So if I take the standard deviation and then square that, I will get the variance, okay? So the first part I'm doing is the residuals, okay? So remember, this is the variance of the residual, and I compute it, it's 11.479, okay? So that's this part, okay? The variance of the residual part, okay? Now, if I'm trying to get the variance of the fitted value, right? That's the same as I do the standard deviation and then square that, okay? That gives me 1.12, okay? So that's the variance of the fitted value, okay? And the last piece, like I said, is the variance of the y, which is the observed, okay? So let me compute that using the standard deviation first, okay? So that's the standard deviation of the height, the column of the child, right? And then square that. So let me do that, okay? That's 12.797, okay? And then just right above it, I added, I can do either way, I guess. So right now, if we try to verify if this is true, we simply add those two together to see if it equals to the last one. Okay. And the way to do it, well, just use Python as a calculator, and you can see that it's fairly close. Okay. So this is what we mean by, well, I hope you can be convinced using this numerical verification, okay? But at the end of the day, as you can see that the correlation coefficient is really important, right? In linear regression, okay? We use it, first of all, if you remember, to compute the slope, okay? And now we start to use R, or absolute value of R, right? To show how the standard deviation of theta value over the standard deviation of Y is. And now with squared of that, which is R squared, we're able to explain, so let me just come back to the slide really quick. We're able to explain the amount of the variance of Y can be explained by the variance of the fitted value. Okay, and the one last thing that we did is that, well, because the sum of them, right, the sum of the residual, the sum of the variance of the fitted values, the sum of the variance of fitted values and that of the variance of residuals equals to the variance of Y, right? And because of that, we're able to now verify that the variance of the residuals over the variance of Y is 1 minus R squared. And then that finally gives us this result. Okay, so R, which is the correlation coefficient, it probably does not look as important as we thought, I guess, when we first introduced it. Okay, but now I hope you start to appreciate the important role it plays, not only just to understand the linear relationship, how strong it is between the two variables, but also at the same time of how all of the important pieces of linear regression that we need to know, many of them rely on this correlation coefficient, okay? Alrighty, so the last part here is really just to demonstrate that, well, now we know the variance of the Y is the sum of the two, right? And then we can also work on the residual side, right? So the standard deviation of the residual is gonna be square root of Y, 1 minus R squared times the standard deviation of Y, okay? So what I'm doing here, nothing fancy. So R in this case is 0.32. Okay. And then if I'm able to compute, right, using this result, okay, I'm doing the square root of 1 minus R squared times the standard deviation of Y, okay, which is what we think the standard deviation is going to be of the residual is going to be, okay, using the math, okay. But then we can also using we can also be using the actual data, the residuals, right, and then we get the standard deviation, which is very close, right? Like only, I don't know, the 20th decimal point is different. Everything else is the same. So I hope this does justify, okay, what we're doing here and why we can be doing this, okay? All right, so all of this, like I said, we try to talk about them mathematically first, and then we verify everything using Python with the data set. And like I said, if you do it without the data sets, you're going to arrive at the same conclusion, okay? Because this is, put it simply, it's just what's behind linear regression, okay? And whichever data you're working with, this kind of properties stay, okay? So we're going to end this topic with a discussion question, okay? While this is fictionist because we don't have exams in this class, we have like those individual projects. But let's just say, okay, let's just say in a class, the midterm exam has an average of 70, okay, standard deviation of 10. The final is an average of 60 and standard deviation of 15, okay? I'm telling you that these two variables, or the two variables, X and Y. So X is the midterm, okay, Y is the final. We're trying to see, I guess, if we can predict the final using the midterm. And the other piece of information now you know is that, well, it is really, the correlation coefficient is really useful, right? So I'm going to tell you that, which is 0.6, okay? The question is fill in the blank. For at least 75% of the students, the regression estimate of final score based on midterm score will be correct within blank points, okay? So take some time to think about it. And well, what we have covered today will be definitely useful, okay? But at the same time here, you might be wondering, where did this 75% comes from? I would just say that check out the Chebyshev's rule that we talked about when we introduced like normal distribution, okay? Because that's where we talked about, well, about certain percentage points going to be within certain number of standard deviations, right, from the mean, okay? So this is going to be a relatively, I guess, maybe a little bit challenging question. So let's spend maybe 5 minutes in the breakout room. And let me, okay, all right. So I'm going to share my screen where we have this question. Okay, so any thoughts? Anybody wants to share what you have discussed? How to, I guess, well, there are multiple steps of this question. Okay, so what we have learned today is useful. And like I said, I had a hint of doing the Chebyshevs in order to figure out that 75%. So I guess that will be the last step. Okay, so any thoughts, any suggested approach that we can take here? The question is asking the regression estimate of the final score based on the midterm score, which is the predicted, okay, or the estimated, the fitted value, okay, will be correct to within certain points. Okay. Any thoughts? Or like, even if you didn't figure it out, like initially how you approach this with your team members? Anyone? It's a multi-step question, so we don't need to solve everything in one try, of course. So if you have anything to share, that would be great.
We knew that the 75% like had something to do with like the number of standard deviations.
Yeah, that's 75%. Yeah. So I also just opened actually, and there's a Chebyshev's bounds. Like I typed in the announcement earlier that is related to, you know, how many standard deviations away. Okay. So in fact, okay, it is just going to be 2 standard deviations away. Okay. So for that's 75%. Okay. So this is what Chebyshev's told us before. And in that case, I guess with Mike's help, we are able to at least phrase this question figuring out 2 standard deviations, right? Like within 2 standard deviations, okay? So I guess my next question for everyone is that, what is the standard deviation we're computing here? We're given, okay, the standard deviation of X, which is 10, okay? We're also given the standard deviation of Y, which is 15. Have we used any of these 2 standard deviations? Or we're trying to do something else? Anyone? So we do know the standard deviation of X, okay? Standard deviation of Y. The question is asking the regression estimate of the final score based on the midterm score will be correct within, in this case, 2 standard deviations, okay? So what does it mean to be correct within what standard deviation? If it's correct, or like 100% correct, meaning that, well, there's no residual, right? The predicted value is perfect, perfectly fitted with the, or the fitted value is perfect for the observed data, okay? So if we take that as, well, being correct, like 100% or like absolutely correct, then we can probably figure out that what this question is asking, now we know it's 2 standard deviations. That standard deviation that we're trying to compute here is this, like 2 times that standard deviation, and then that standard deviation that we're trying to compute is the residual standard deviation. Okay, so remember, residual is trying to evaluate how close our fitted value is to the observed. Okay, and then when we want to say that we want to be correct within certain bounds, then it is talking about the standard deviation of the residual. Okay, and now if we come back to what we have just learned, the standard deviation of the residual is the square root of 1 minus r squared times the standard deviation of y. Okay, so mathematically, I guess what you can do is that standard deviation of y is 15, right? I can use 15 times square root of 1 minus r squared, where r is 0.6. Okay, then that will give me the standard deviation of the residual, and then I times 2, which will give me be correct within how many points. Okay, so yeah, you can do that by hand, but I'm just also going to show you here how you can do it by Python. Well, we're really just using Python as a calculator here. We have our r to be 0.6. Okay, the standard deviation of y is 15. So this, the residual, standard deviation of residual, as we know, is the square root, right, of 1 minus r squared times the standard deviation of y. So once we compute it, it's going to be 12. Okay. And then the second part is the Chebyshev's inequality. And we realize that, well, for us, it's going to be 75% is going to be within 2 standard deviations, right? So we simply do 2 times that 12 that we computed, which is going to give us 24. Okay. Yeah, so I think this question is, you know, synthesizing a lot of stuff that we've learned. I mean, most recently, the variance decomposition that we talked about, but also like going back to Chebyshev's inequality, I guess that's topic 20, when we first introduced how you're able to approximate those kind of probability. Okay, so keep in mind that a lot of the, especially towards the end of the semester, a lot of the stuff is synthesizing. So be prepared, but also I hope, because we list everything on the website with different links. So hopefully it's easy for you to also navigate all of the previous material as well. Okay. Alrighty, so